Okay, now we're going to talk about orthogonal vectors. Now, we've been talking about inner product, which is inner product is like dot product, right? And we've been talking about norm, which is like length. Now we're going to talk about orthogonal, which is like perpendicular. Okay, these are all properties that have meaning in the geometry of three-dimensional space. And the wonderful thing is that we can generalize these properties to n-dimensional space. Now you have some idea of perpendicular, so we're going to use that idea to generalize. Okay, so here we have the definition of orthogonal vectors. Vectors are orthogonal if their inner product is 0, which is uv equals 0. Now, for instance, I think that you may have the idea that the vectors 1, 0, 0, and 0, 1, 0, and 0, 0, 1. These are three perpendicular directions in three-dimensional space. And if I use this definition on any pair of these vectors, I'm going to get 0. Think about the inner product of 1, 0, 0 with 0, 1, 0. Well, for the inner product, I take first times first, which is 0, plus second times second, which is 0, plus third times third, which is 0. The inner product of these two vectors is 0. Same with these two vectors. Take the inner product. First times first is 0, second times second is 0, third times third is 0. Add them up, you get 0. The inner product of those two is 0. Any combination of inner product of two vectors in this set is going to give 0. So all of these vectors are orthogonal. Okay, so let's do an example with complex vectors. It turns out if you do the inner product using the usual rule, first conjugate times first, that's this term here, plus second conjugate times second, that's this term here, plus third conjugate times third, that's this term here, plus fourth conjugate times fourth, that's this term here. If you work all that out, it's probably easier to do using Sage, you'll get 0. Now it turns out that that means that these two complex vectors are orthogonal. Okay? All right, now here we talked about two vectors being orthogonal. We can define an orthogonal set of vectors. In fact, the example that I gave up here of 1, 0, 0, 0, 1, 0, 0, 0, 1, this is an orthogonal set. Why is that? Because any pair of vectors is orthogonal. And that's what the definition says. If we have a set of vectors, then this is an orthogonal set if every pair of vectors from S is orthogonal. Okay. Now here he's using this same example that I gave above, but generalizing. He's saying, take these column vectors and think of the ith vector in this set. The ith vector has a 1 in the ith place and 0 everywhere else. Okay, so if I take, for instance, if I take C5 and I take this set of standard vectors, I'm going to get E1. Let's follow the prescription. Well, E1, the component of E1, the first component of E1 is 1 because the first component is equal to the index of the vector. So I'm going to get 1 here. And then all the others are 0. Okay. If I look for E2, well, E2, that means I is equal to 2. And that means I get a 1 in the jth component when j is equal to 2. So that means in the second component, I'm going to get a 1. All the others are 0s. You can do the same thing with E3. E3 means that I is equal to 3, and I'll have a 1 in the third place and 0 everywhere else. 0, 0, 1, 0, 0. If I do E4, it's going to be equal to 0, 0, 0, 1, 0, and then E5 is 0, 0, 0, 0, 1. Okay, so I get a set of 5 vectors. In m-dimensional space, you'll always get a set of m standard unit vectors. Okay. Now notice, as you see my example here, that in fact the jth vector in this set is equal to the jth column of the identity matrix. Look, this first column, second column, third column, fourth, fifth column of the identity matrix. Okay. And here he goes through an example of what should be pretty clear from this example, that if I take the inner product of any two of these vectors, I'm going to get 0. Why? Because whenever this one has a non-zero entry, all the others have a 0 entry. Okay? And the same with all the others. Okay? Now here's another example of an orthogonal set. Here it's much more difficult to prove that this is these are orthogonal. Here he goes through and does all of the inner products. Well, he doesn't do all of them, he does 2 of them. But you can show all the inner products on this. Now here's an important theorem. Orthogonal sets are linearly independent. Very important theorem. Okay. And in this case, for instance, in the case of these vectors, you can see that they're linearly independent because they form the columns of the identity matrix. Right? And we saw before that if a matrix is non-singular, then its columns form a linearly independent set. So these vectors do form a linearly independent set, but in fact this is true in general. Whenever I have n orthogonal n-dimensional vectors, well, they don't have to be n-dimensional. Whenever I have n orthogonal vectors, they're always linearly independent. And the proof of this is very ingenious. Suppose I have a linear dependence relation. I take this linear dependence relation and I take the inner product of both sides with each one of these in turn. Okay? So if I take the inner product of this linear dependence and take the inner product with u1, then I'm going to get a1, u1, all the other terms are 0. So if I take the inner product with u1, that will get me that a u1 is equal to, well, I take the inner product of u1 with 0 over here too, which is equal to 0. Right, but I know that this here must be greater than 0. That was something I proved before. So that means that alpha, and that should be alpha 1. That means that alpha 1 must be 0. Okay. I could do the same with any vector u. For instance, if I took u3, if I take the inner product of u3 on this side, and I take the inner product of u3 on this side, here all of these terms except for the u3 term are going to give me 0. The u3 term will give me alpha 3, and on the right-hand side I get a 0. So I get alpha 3 equal to 0. Now he organized the proof slightly differently, probably is a little more systematic than I am, but that's basically the idea. You take the inner product of this equation with each vector one at a time. Okay, so pretty cool proof, pretty important result. Orthogonal vectors mutual orthogonal vectors are always linearly independent. And we'll use that later on. Okay, that's it.